Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
Today's part 2 of 4 parts of QbD with the theme of discussion is turning biological hypotheses into quantitative maps. This part outlines a systematic framework for applying quality by design (QbD) principles to bioprocessing, specifically within fermentation. It describes how to transform biological hypotheses into quantitative process maps by identifying critical process parameters (CPPs) through both mechanistic understanding and statistical modeling. The discussion emphasizes the use of design of experiments (DoE) to efficiently explore interactions between variables like temperature, pH, and oxygen transfer. These methodologies help define a multivariate design space where product quality is consistently maintained. Ultimately, the source advocates for prioritizing robust operating windows over fragile optima to ensure process reliability during scale-up. This structured approach ensures that biomanufacturing stays within regulatory and scientific boundaries throughout a product's life cycle.
Welcome to The Debate. Today we're tackling what is, I think, the single hardest problem in bioprocessing: the translation gap. We're discussing Lesson 2, which is all about turning biological hypothesis into, well, quantitative maps.
And the real question on the table is whether we can actually map the chaos of biology. I mean, the industry is obsessed with these statistical frameworks, design of experiments, design space, all of it. But I'm here to ask if these, mathematical cages are really strong enough to hold a living, breathing, evolving organism.
And I'm here to argue that without those cages, you don't have a process. You have an art project. We're talking about the plumbing of the quality by design operating system. It's about moving from these vague theories to concrete critical process parameters. I'm the advocate.
And I'm the dissenter.
Okay, so let's start with the stakes here. In traditional biotech, process development was often just tribal knowledge. You'd have the guru who knew that if the broth smelled a certain way, you'd add more glucose. That is just not a scalable industry strategy. So my position is that we have to replace intuition with structure. We need to identify these critical process parameters, CPPs, and link them mathematically to the product's quality. We're building a map that regulators can trust and that, engineers can actually control.
The map is a very seductive metaphor, I'll give you that. But maps are static, and biology is dynamic. My position is that while DoE, design of experiments, is a useful tool, it creates a dangerous false sense of security. You can produce a beautiful 3D surface plot that tells you exactly where to run your bioreactor, and the cells will still crash. And why? Because statistical maps so often hide these biological cliffs. I'm arguing for a robust operating window that respects the physiology rather than some mathematically perfect optimum that just ignores the messiness of scale.
Messiness is just a word for unmeasured variables. But let's get into the mechanics of how we clean that up. Because the core of Lesson 2 is selecting the CPPs. We aren't guessing here. We have canonical candidates: temperature, pH, dissolved oxygen, feed rate. These are the levers we pull. The advocate's view is simple. If you can control the inputs, you can predict the outputs.
Okay, but are they inputs or are they requests?
They're set points on a controller.
On a controller, sure. But let's look at the distinction the material makes between kinetically limited and transport-limited parameters. This is where the math, frankly, usually breaks down. You view temperature as a knob. You turn it down, growth slows, protein folding improves. That's kinetics. It's a chemical reaction rate. And that works fine in a test tube.
It works in a reactor, too. I mean, the Arrhenius equation doesn't just stop working because the tank is bigger.
The equation works, but the environment changes. Let's talk about the transport-limited side. This is the physics mixing, heat transfer, and especially oxygen transfer. You mentioned feed rate as a CPP. You might have a statistical model that says high feed rate equals high biomass. Great. But if you scale that up and your large tank physically cannot transfer oxygen fast enough to match that feed.
You're talking about KLA, the volumetric oxygen transfer coefficient.
Right. KLA. It's the bottleneck. If you ignore that transport limit, your so-called optimized feed rate drives the cells straight into overflow metabolism. They just can't burn the carbon fast enough because they can't get the oxygen. So what do? They dump acetate or lactate. The pH crashes. The cells stress out.
Your statistical map said high yield, but the physics said system failure.
That's a valid constraint, but I think you're conflating bad engineering with bad statistics. The whole point of a rigorous design space is that it accounts for interactions. If KLA is a limiting factor, we include dissolved oxygen, or DO, as a parameter in the design. We don't ignore it, we map it. We can model the interaction between feed rate and agitation speed to predict exactly where that oxygen crash is going to happen.
You can. But do people do it? Most people just treat DO as a set point. Keep DO at 30%. But in a 20,000-liter tank, you have gradients. You have dead zones. The probe might read 30%, but the cells at the very bottom are suffocating. My point is that transport parameters, like agitation speed, gassing rate, even reactor geometry, often determine the biology more than your kinetic recipe does, and those are very, very hard to model in the small-scale DOE.
And that is precisely why we have scale-down models. But let's step back to the methodology, because I think the solution to your fear of these cliffs is actually better math, not less of it. We need to talk about experimental architecture. How do we build this map?
Usually by burning through a lot of money on experiments that don't tell us nearly enough.
Or by being smart about it. The standard approach is a funnel. You start with screening designs to filter out the noise. Then you move to optimization designs to actually build the map. The material brings up Plackett-Berman designs for screening.
Which, I have to say, are incredibly risky for fermentation.
They're efficient. If you have 20 potential factors, media components, temperature, shift timing, you just can't test them all. Plackett-Berman lets you identify the heavy hitters with very few runs.
But at what cost? Plackett-Berman designs assume that main effects dominate. They assume interactions are negligible. In biology, everything interacts. If temperature only matters when the pH is low, a Plackett-Berman design might just wash that effect out completely. You get a false negative. You throw away a critical parameter because the math assumed the world was simple.
I'll grant you that Plackett-Berman is a blunt instrument. That's why the industry is moving toward definitive screening designs, or DSDs. And this is a massive leap forward. DSDs break that aliasing problem. They let you see the main effects, and they give you a signal if there's curvature, if the relationship isn't just a straight line.
Can you explain curvature for the listener who isn't a statistician? I mean, why should they care if the line is curved?
Curvature is the mathematical signature of a biological limit. A straight line sort of implies more is always better. Higher temp, faster growth, but we know biology creates parabolas. Higher temp is better until the protein starts to unfold, then it gets much, much worse. That peak is a curve. DSDs can detect that quadratic effect with a fraction of the experiments needed for a full factorial. It's the efficiency of screening with the insight of optimization.
DSDs are better, I'll admit that. But there's a trap in screening that isn't about the math. It's about the metric. In screening, everyone obsesses over titer, yield. Does this factor make more stuff?
Titer is usually the primary objective, yes.
But quality is the constraint. You might screen out a factor because it didn't improve the titer. But unbeknownst to you, that factor was absolutely critical for keeping host cell proteins low, or for preventing aggregation. If you screen based only on yield, you might bake a quality problem into your process that you won't find until it's way too late.
Well, that's a failure of execution, not of the framework. The whole QbD approach explicitly demands we link parameters to CQA's critical quality attributes right from the very start. We should be measuring aggregates in the screening phase. But let's say we've done that. We have our significant factors. Now we need the high-resolution map. We move to response surface methodology, RSM. This is where we use things like central composite designs.
And this is where we kill the cells. You're being very dramatic today. We aren't killing them. We are stressing them to define the boundaries. No, literally. Look at the geometry of a central composite design. It has a center point where you think the process works, and then it has these star points, extreme values that stick way out of the box. You might have a run that combines your highest possible temperature with your highest possible pH.
We need to know what happens at the edges. That's how you prove robustness.
But in a biological system, those corners aren't just low yield, they're lethal. If you run a bioreactor at 40 degrees C and a pH of 8, the culture dies. You get zero data. Or worse, you get garbage data, lysed cells, proteases everywhere. You can't model a surface if half your data points are from dead batches.
That's why I'm a much bigger fan of Box-Benken designs.
Because they play it safe? Because they're realistic. Box-Benken designs place their points at the midpoints of the edges. They avoid the extreme corners. They allow you to map the curvature and the interactions without, effectively autoclaving your product during the experiment. It acknowledges that biological viability is the ultimate constraint on your statistical design.
Box-Benken is a valid choice, I agree, specifically if you already know the edges or cliffs. But let's look at what these designs, either of them, give us. They give us the power of ANOVA, analysis of variance.
Ah, the magic p-value.
It is magic, in a sense. It separates signal from noise. We can look at the F-test and say, with mathematical certainty, this interaction between feed rate and temperature is real. It is not random chance. And this gives us a transfer function, an equation, y equals f of x, that predicts quality. This is the holy grail, isn't it? The design space defined by ICH-Q8. If we're inside this mathematical space, we're compliant. We can move set points without asking the FDA for permission.
That's the regulatory promise. But I want to challenge the interpretation of that mathematical certainty. You get a p-value that says the interaction is significant. Great. But what does it mean?
It means the effect of one factor depends on the level of the other.
That's the statistics definition. I'm asking for the biological definition. If you have a strong interaction term in your model, that is the cells screaming at you. It usually signals a regime shift.
Walk us through that. What is a regime shift?
It's a switch in metabolic strategy. Let's go back to the feed rate and oxygen example. At low feed rates, the cells are carbon limited. They eat every molecule of glucose you give them. But as you increase the feed, you cross a threshold, that interaction with KLA, where they become oxygen limited. That is a regime shift. The biology changes fundamentally. The statistical model sees this as curvature, or a significant interaction term. If you just treat it as a number, you miss the risk. You might set your operating point right on the edge of that switch.
But the model captures the switch. That is the beauty of the response surface. We can see the topography. We can see where the hill drops off.
You see the drop-off in the numbers, but do you understand the mechanism? The material warns us, and I'm paraphrasing here, a statistical interaction without a biological mechanism is just a coincidence. If your model says high salt improves titer, you better know why. Is it osmotic stress? Is it preventing lysis? If you don't know the why, you can't defend the what when things go wrong at manufacturing scale.
I agree that interpretation is key. The goal isn't just an equation, it's a narrative backed by data. For example, if we see an interaction between induction timing and temperature, the narrative is likely about protein folding kinetics. Inducing early at high temp might be fine, but inducing late at high temp crashes the oxygen. The math flags the crime scene, the biologist acts as the detective.
I like the detective analogy, but let's talk about the verdict. The outcome of all this work is supposed to be the optimum. You use a desirability function, a mathematical formula, to find the single best set of conditions. Maximize titer, minimize aggregates.
Correct. Why would we ever settle for less? We want the highest productivity possible.
Because optimization often leads to what are called fragile optima. Picture a mountain peak. It's the highest point in the landscape, but it's a needle. The summit is 2 feet wide. If you stand there, sure, you're at the optimum. But if the wind blows, if your raw materials vary slightly, or your pH probe drifts by 0.1, you fall right off the cliff.
So you're suggesting we should just camp out in the valley?
I'm suggesting we look for a plateau. I want a robust operating window. Maybe the titer is 5% lower than the absolute peak, but the ground is flat. If the agitation speed wobbles or the glucose concentration in the feed is slightly off, the product quality doesn't change.
But doesn't that sort of defeat the purpose of high-performance bioprocessing? We're just leaving money on the table.
You lose a lot more money if you lose an entire commercial batch because you are operating on a razor's edge. The material talks about this tension. Fragile optima usually reflect a conflict between competing mechanisms, like productivity versus stress. Pushing cells to their absolute metabolic limit is inherently unstable.
I see your point, but I do believe modern control strategies can handle a lot of that instability. However, I will concede that the very definition of design space allows for this. The design space isn't just a single point, it's a region. We can define that region using probability. We can use Bayesian methods to say, inside this box, we have a 99% probability of meeting specifications.
Probability is the key word there.
Exactly. We can construct the design space to be that plateau you want. If the peak is too sharp, the probability of success drops because of the variance. So the math actually guides us away from the fragile peak and toward the robust center, provided we set the acceptance criteria correctly.
If, and it's a big if, you account for the variability of the inputs. Which brings us to the final layer of complexity, raw materials. We often treat media like it's a constant, but it's a mixture.
Ah, mixture designs, right. This is a specialized part of DoE. We use things like simplex lattice designs to optimize the ratios of carbon, nitrogen, and trace elements.
Which is a complete nightmare, because changing one component changes the ratio of everything else. And here's where the fragile optimum is most dangerous. If you optimize your process using lot A of yeast extract, and then you buy lot B, which has slightly less magnesium.
And that is why we don't just optimize, we characterize. The design space is supposed to cover that variability. If we know lot B is low in magnesium, the design space tells us how to adjust the process parameters, maybe raise the temperature or change the feed rate to compensate. That is the ultimate flexibility. The map allows you to navigate around the pothole,
Provided the map is accurate, and provided you recognize that the edges of that map are not just statistical confidence intervals, but real biological cliffs.
I think we found the synthesis here. The statistics provide the structure, the plumbing, as I called it at the start. But the biology provides the logic. You really can't have one without the other.
Exactly. A p-value tells you that something happened. Mechanism tells you why. And robustness tells you if it will happen again next week.
So, to summarize Lesson 2, we must move from hypothesis to map. We use rigorous DoE like definitive screening designs and maybe central composites to identify the critical process parameters. But we have to ensure those parameters are mechanistic, not just settings on a screen.
And we must interpret those maps with a healthy skepticism. We need to look for the transport limitations that the small-scale models might miss. And we need to prioritize robust plateaus over those fragile peaks.
The design space is the goal, yes, but it must be a space where the biology is comfortable, not just where the math works out perfectly.
So as you look at your own process data, ask yourself, is this statistically significant or is it biologically meaningful? You absolutely need both to be safe.
And that brings us to the end of this examination of quantitative process mapping.
We hope this debate helps you navigate your own design spaces with a bit more confidence and a healthy dose of paranoia.
That's it for the debate.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.